Okay, I'll get started. I hope you can hear me. I wanted to just remind you, first of all, about ways to contact me. So my office phone number is here, but this should be a 7, actually, not a 6. So it's not my office phone number. My email is gorange@pa.uky.edu, and here are my office ads. But if you can't make the office ads, just send me an email, and I'll work out another appointment time with you. This is the homework schedule that we're working with. It's a weekly homework schedule. So Tuesday's lecture class introduce some material. Today's lecture class will introduce some material. You'll cover homework on those materials in next Monday's recitation class, and the assignments for that homework, which is a numerical answers in WebAssign and a fully worked out problem on Canvas. They're due midnight on next Monday. Any questions on that before I go on? Okay, one little thing I realized about chat, Zoom chat, and your questions last time, because I may have missed some of your questions. One reason that might have happened was that I'm using 2 computers, and if you were to send any questions to everyone, then whatever computer I'm looking at, I should be able to see the chat and better respond to your questions. So that was just a thought I had about last class if I missed questions. I mean, there's another reason I can miss questions is that I just missed them, but that was one concrete reason I missed questions. So last class, we introduced electrical attraction, electrical repulsion. We introduced electrical charge, positive, negative charge. Today's class, I want to build on our work last class about electrical attraction and repulsion, and I want to work towards a quantitative description of the attraction and repulsion, or quantitative description of the electrical force. We're going to introduce what's called Coulomb's law for the electrical force. It's kind of the equivalent of Newton's law for the gravitational force. We'll see a number of ways in which it's similar. We'll see a number of ways in which it's different. I'm going to introduce what's called the principle of superposition for electrical forces, and that's actually analogous to a principle of superposition for gravitational forces. And superposition principle in electricity or magnetism or gravity is key to being able to solve problems involving electricity, magnetism, gravity. So that's important. And then finally, through today's class, we'll look at some illustrations, example problems that involve electric forces and electric charges to get more familiarity, to get some practice in solving electrical problems. So that's the plan. Today's class does involve something that you first met in Physics 211, or I mean, you may have met it before, it's Physics 211, and that's vectors. And one thing we'll do today is work with some vectors. One thing we'll do today is work with vector additions. So I'm just letting you know that up front. Okay, so Coulomb's law, law of physics, is the law of physics describing the electrical force between electrical charges. And so that's what we're going to introduce first here. Let me say a few words about Coulomb. He's dead now. He was alive, you know, a couple of hundred years ago. He was so interestingly, he was an engineer and physicist. Actually, he worked as an engineer, and he worked on things that we met in physics 211, you know, the forces on beams, the strengths of materials. That sounds like sort of physics engineering stuff from physics 211. His hobby, on the other hand, his hobby was investigating electricity and magnetism, the forces of electricity and magnetism. And that sounds like 213 stuff. So Charles Coulomb kind of parallels our walk through physics 211, physics 213 in his work as an engineer and his hobby as a physicist. So he quantified the electrical force between electrical charges, that attraction repulsion between electrical charges, by making measurements of electrical forces between electrical charges with an instrument or a device that we call a torsion balance. Let me get my pen going here if I can. Oh, I didn't mean to do that. So over here on the left is a torsion balance. And so what is a torsion balance? Well, in a torsion balance, you have this long, it's vertical here, long, thin wire hanging vertically, and suspended from the wire is this horizontal beam. And there's masses or objects on either end of the beam to balance the beam. Next to the beam is another object in blue here. And if you put charges on the blue and red object on the torsion balance here, what will happen? Well, if you put a pair of charges on the blue and the red sphere here, the blue and the red object here, you'll get, you know, an electrical attraction or electrical repulsion. And depending on whether it's electrical attraction, electrical repulsion, it'll twist the torsion balance. It'll twist the arm, it'll twist the wire either clockwise or counterclockwise. And you can measure, Coulomb uses to measure the strength of the electrical attraction or electrical repulsion between these pairs of charges by measuring the amount that the torsion balance twisted, measuring the amount that the wire twisted. So that's how the torsion balance works. What he really did is a beautiful experiment. It's actually a very challenging, difficult experiment, but he took his engineering expertise with beams and wires and materials, all that stuff, and applied it to his hobby of electricity and magnetism to measure electrical forces between electrical charges. And that's how it all worked out. Now, I got a little video. I want to show you how it works in a little more detail, or in a little animation. So I'm going to share a different screen here, if I'm capable. Okay, so I hope you can see a little video here, and I'm just going to play. It just takes a minute or so. And what we're looking at in this screenshot is a torsion balance for measuring electrical forces between electrical charges. Here, vertically, is the long, thin wire. And here in the center, you can see the two, I think you can see the two spheres on which we can place charges and measure the forces between the charges. One of them is attached to the wire, and one of them is not attached to the wire. And that allows us, through the rotation of the wire, the twisting of the wire, to see the, to measure the forces between the two charges. So let's play the little animation. Here we see it a little more clearly. There's a stationary sphere on the left, and there's the sphere that can rotate on the right. And now we're bringing in some charge, and we're going to drop the charge onto the sphere. And we see, in this case, there must be like charges we've just applied to both spheres. And now the spheres are repelling one another. And so the sphere that's capable of moving, the sphere that's on the horizontal beam, that twists out of the way. Here you're seeing in detail the twist of the wire. And it's by the amount of twist of the wire measured by the scale on the side of the apparatus that you can determine the force. And you could imagine, right, that you could do this little experiment for different quantities of charge. You could do it for, measure different separations between the charges. You could do it for attraction and repulsion. And in that way, you could really explore the electrical force and quantify the electrical force between electrical charges. And that's what that's what Coulomb did. Okay. Well, that's the experiment. Now I want to go to the law, right? We're going to write down the law. We're going to talk about the law that he derived from the experiment, that he derived from the torsion balance. So I want to go back to sharing the other screen. Here we are. And let's jump to the next slide. So what properties of the electrical force did Coulomb find? Let me be a little bit specific here. Coulomb's law is about the electric force between point charges. Now, of course, point charges didn't really exist in his experiment. A pair of point charges didn't really exist. But an approximate point charge is when objects are small enough that compared to their separation, they kind of look like point charges. So that's really the circumstances that we're thinking about. In the Coulomb experiment, in the torsion balance experiment, they weren't point charges, but the sizes of those little spheres on which we put the charges were much smaller than the separations between the two spheres. So it's approximately point charges, and he could explore the law between point charges in that way. He found a bunch of features. So firstly, he found that the force between 2 point charges is inversely proportional to the square of their separation. So that means if you double the separation, the square of the separation will go up by 4. The inverse of that will go down by a factor of 4. So if you double the separation, you get a 4 times smaller force. If you were to triple the separation, well, the square of that is 9, so you get a 9 times smaller force. And that's a pattern. That's the inverse square law of the electrical force between electrical charges. And you might recall that it parallels the inverse square law for the gravitational force between masses. So that's one important feature. The force is proportional to the sizes of the two charges. So if you make one charge bigger, or the other charge bigger, or both charges bigger, the force will get bigger in proportion to the product of the sizes of those two charges. And that's what I've written on this overhead here. Q1 is charge number 1, Q2 is charge number 2, and by the vertical lines, I'm indicating the magnitude of the charges, the size of the charges. And that's going to determine, that product's going to determine the size of the force. That's also like gravitational force, right? Gravitational force depends on the two masses. It's in proportion to the product of the two masses. The force acts along a line between the two charges. So imagine drawing a line between the two charges. Think about that line. The attractive force acts along that line, pulling them together. The repulsive force, if there's like charges, acts along that line, pushing them apart. So the forces, electrical forces, are always along that line, either attractive or repulsive along that line. And then finally, well, we already knew this, but it's built into Coulomb's law, that if you have opposite charges, a plus and a minus, then that's an attractive force. If you have like charges, so that could be two pluses or two minuses, then that's a repulsive force. And so these are the ingredients, these are the components of Coulomb's law. Coulomb wrote down an equation for his law. As I talk about the equation, I'm going to introduce a little bit of notation here. So let me get the pen going again. In this little picture on the left, right, what are we seeing here? We're seeing a charge we called Q1 over here. We're seeing a charge we call Q2 over here. We're seeing them separated by some distance, we've called that R. And if these are like charges, two pluses or two minuses, then you get a repulsive force. And we're seeing the repulsive force experienced by charge Q1 on the left, the repulsive force experienced by charge Q2 over here on the right. So that's the case of electrical repulsion that Coulomb's law will describe. Law also describes electrical attraction. So here's the case of electrical attraction. In this example, again, we've got two charges, Q1 over here on the left, Q2 over here on the right. Now they're opposite charges, a plus and a minus. They're separated by some distance, we'd call it R again. And we see the forces of attraction between the two charges. So Q1 is attracted to Q2 and Q2 is attracted to Q1. Those are those forces. And so this is going to be a little bit of notation that we're going to use to introduce Coulomb's law. And so here's the law. Specifically, the way I've written it here, this is the law for the strength, the size, the magnitude of the electrical force. We'll talk about the direction, the orientation in a moment. The force is over here on the left-hand side. So here's the force. And here, over here on the right-hand side, are the things that force depends on. So the force is an inverse square law. So here's the separation between the charges squared in the denominator of the equation. The force depends on the product of the sizes or magnitudes of the charges. Here's the product of the sizes or magnitudes of the charges in the numerator. And then there's a constant. That's this constant here. It's called Coulomb's constant that sets the scale, sets the overall size, sets the overall magnitude of the force between the pair of charges. And so this is Coulomb's law. It's quite a simple equation. It's a nice succinct equation that summarizes all those points I made from the previous slide. Just a couple of points, bullet points about it. Now that equation, as I say, I've written that equation as an equation for the size or the strength of the force. The force itself is a vector. It has a magnitude, it has a direction. So the force itself is either attractive or repulsive along that line that joins the two charges. Also importantly, and this is, consistent with Newton's third law, and all forces are consistent with Newton's third law. That's the law of action and reaction, that forces come in pairs. If you look upstairs here on the left-hand sketch, the force on Q1, which we called the force of 2 on 1, charge 2 on charge 1, that's equal and opposite to the force on charge 2 that we called force 1 on 2, force charge 1 on charge 2. So those two forces are equal and opposite, consistent with Coulomb's law. And over here on the right, in the case of attraction, the two forces on the two charges, they're equal and opposite, consistent with Coulomb's law. Their strengths are the same, but their directions are opposite, 180 degrees to one another. Okay, let me just make a couple of comments on Coulomb's law. So there's a constant in Coulomb's law. We just mentioned it. It's the Coulomb constant. It parallels a constant in Newton's law of gravity. That was Newton's constant, or the gravitational constant. Now, here I've written down the sizes of those two constants, the numerical sizes of them. Well, Coulomb's constant is a very large number. It's about 9 times 10 to the 9 billion Newtons meters squared per Coulomb squared. On the other hand, gravitational constant, that's a really tiny number. It's about 6.7 times 10 to the minus 11 Newton meter squared kilogram squared. So the numerical size of gravitational constant and Coulomb constant are very, very different. And that's related to the fact that the inherent size of the gravitational and electrical forces are very different. The electrical force is a monster force. The gravitational force, by comparison, is a very puny force. Now, in our everyday world, we might experience the gravitational force as the big force and the electric force as the puny force. But that's because the electrical force is kind of hidden from us because of there being positive and negative charges, whereas the gravitational force is never hidden from us because there's only positive masses. In everyday experiences, when you take your socks out of the dryer and they're charged up, or when you're working with charges in a little lab experiment in your home laboratory, the sizes of the charges are not coulombs. Coulombs is an enormous amount of charge. They're typically nanocoulombs, maybe microcoulombs. And you might remember that the ultimate packets of charge are electrons and protons, and their amounts of charge, well, that's a really small number in Coulomb. It's 1.6 times 10 to the minus 19 coulombs of charge is the negative charge on an electron or the positive charge on a proton. Finally, I said that Coulomb's law is a force law between a pair of point charges. It actually also works as a force law between two spherically symmetric charge distributions, like two spheres of charge, so maybe two solid spheres of charge, or two spherical shells of charge. Coulomb's law also works in that situation. In that situation, that distance r, which is the separation between the point charges, is now the separation between the centers of the two spheres, or the centers of the two spherical shells. So you can also use it for a pair of spherical shells or a pair of solid spheres. Okay, so we introduced Coulomb's law. Let's do an example of Coulomb's law. That we get familiar with Coulomb's law. We get used to how we can use Coulomb's law. First question here is, I want to, this goes back to what I was mentioning about, you know, the electric force being a monster and the gravitational force being a weakling. I'm going to numerically compare the electrical forces and the gravitational forces between the electron and protons ingredients that are inside an ordinary hydrogen atom. And so I'm just going to think of a hydrogen atom. It's made of a proton and an electron. What is the electrical force between the electron and proton? What is the gravitational force between the electron and the proton? What is the ratio of those two forces? What's the relative size of the electrical force compared to the gravitational force? So here's the information I'm going to use. We've got to use the gravitational constant and the Coulomb constant because those are the numbers that determine the inherent strength the inherent size of electric and gravitational forces. And then we need to know the charges of the electron and the proton. And I just mentioned those charges. They're 1.6 times 10 to the minus 19 coulombs. And then we need to know the masses of the electron and proton. And I'm sure, remember that the electron is very light. It's 9 times 10 to the minus 31 kilograms. The proton, by comparison, is very heavy. It's the scale of, a couple of thousand times heavier. It's 1.7 times 10 to the minus 27 kilograms. And those are the numbers we're going to need. Now, I could have said, well, instead of compare the electric and gravitational forces in the hydrogen atom, I could say, well, compare the electric forces, gravitational forces between 1 Coulomb of charge and 1 kilogram of mass. Now, the reason I didn't say that was that the hydrogen atom was given to us by nature. It's a natural comparison of electric and gravitational forces. If I compare the forces between a pair of Coulomb charges and a pair of kilogram masses, well, kilograms and coulombs are just something we've invented. So it seems more natural to me to take a natural comparison of the force strength. So that's what we're going to do. Okay, so let me do this comparison. Maybe I'll do this on the whiteboard, if I can share the whiteboard somehow. So I'm going to stop sharing this, I think. Okay, I'm sharing my whiteboard. This is going to be a new experiment for me. Extremely nervous right now about it. Mildly nervous. What do I need? I need Coulomb's law and I need Newton's law for electricity and for gravity. So here's Coulomb's law describing the size of the electrical force between a pair of charges. Because I'm wanting to distinguish electricity and gravity, I'm going to put this little e for electricity on that. And then here's gravitational force law for the size of the force between a pair of masses. And so this is really my starting point. And when you write the electric force law and the gravitational force law side by side like this, what always strikes me, and I'm sure right now this is what you're thinking of. Look how similar they look, right? Both inverse square laws, 1 over r squared in both of them. Both involve the products of a dimension of nature, charge for electric force, mass for gravitational force. And both have some characteristic constant, the Coulomb constant or the gravitational constant, set in a scale of these two different forces. So they look very similar. And it's very interesting to think about that. Okay, but getting on with the actual problem now, we want the ratio of the electric force to the gravitational force. So to do that for the hydrogen atom, to do that, all I've got to do is write out the expression for the electrical force. Here it is in the numerator. Write out the expression for the gravitational force. Nearly made a mistake there. How do I get rid of that? Here's gravitational force law. Now, I can see right away that it doesn't actually matter in the hydrogen atom how far apart the electron and the proton are in answering this question about what are the relative sizes of the forces. Because they're both 1 over r squared laws, the 1 over r squared cancels out in our ratio. So that's nice. All I need to do then is to fill in these numbers. And these numbers I wrote on the previous slide, right? We wrote that the Coulomb constant is 9 times 10 to the 9 Newton meter squared per Coulomb squared. We wrote that the charges of the electron and the proton, Q1 and Q2, are 1.6 times 10 to the minus 19 coulombs. That's the magnitude of them. And then we wrote that the gravitational constant was 6.7 times 10 to the minus 11 Newton meter squared per kilogram squared. And we wrote down the masses of the electron and the proton. The scales of 10 to the minus 30 kilograms and 10 to the minus 27 kilograms. So if you plug in all those numbers, I'm not going to write them all out, right? If I try to write them out, well, that's the end of the class. It's going to take me the whole class to write out those numbers. But I did ahead of time, and I even remembered it. Figure out the number. And it's this number here, 2 times 10 to the 39, i.e. the electrical force is a monster. The gravitational force is tiny in comparison. They're different by a scale of 10 to the 39, 10 to the 40. That's a massive, massive difference between these two forces. It makes it all the more amazing that as we walk around our world, as we get up in the morning, right, it seems that gravitational force is the big gun and that electric force is the puny force. But really, electrical force is the big gun and gravitational force is the really weak force. Okay. Let me go back to the slides. And let's look at another problem involving Coulomb's law, second example of Coulomb's law. So let's see if we can do this one. And in this problem, I want to not calculate the force, but I want to actually, by figuring the force, calculate the charge on some spheres that are repelling one another. So let me show you a demonstration of this, if I can do that. But there's no expense spared in this lecture. I made this myself. I've got these two little objects, two little spheres hanging from two strings. And right now they're uncharged. And the strings are just hanging vertically. Now what I'm going to do is I've got a piece of plastic pipe here. I found it in the basement. And I've got, we used to have a cat. Here's the fur from it. And I'm going to charge up the plastic pipe with the cat's fur. And then I'm going to, by contact, charge up these two spheres. When I charge up the two spheres, I'll be charging them equally, putting the same type of charge on the spheres, positive charges or negative charges. I can't remember which way around it is. And we're going to see them repel. And what we're actually going to do is calculate the charge on these charged spheres by observing their repulsion. Kind of like a version of, you know, a poor person's version of the torsion balance experiment that Coulomb used to measure forces. We're going to measure charges in this case. So I've got to do this charging up by rubbing. And we know we're right now ripping off those electrons and putting them on the piece of plastic pipe. And now I'm going to charge up the two spheres. And now look, they're not hanging vertically. You can see the space between them. I hope you can see that. That's because they're repelling one another. There's an electrical force of repulsion between these two spheres. And we're going to calculate this. We're actually going to calculate the electrical force, and from that be able to calculate the electrical charge that I've deposited on these two spheres. And that's an interesting question. You know, how much charge did I just stick on them? Is it, you know, a nano-coulomb, a micro-coulomb? A Coulomb, a megacoulomb? Well, we're going to find out the answer to that question. Okay. I hope you saw that, because I hope you see me, because I didn't actually stop sharing the slide, but I think you probably saw me do that experiment as a little inset. I see now some questions have appeared in the chat. So let me first, before I solve this problem, try and answer those questions. I dropped my pen. That's what I wasn't running away from the questions. I just dropped my pen. Okay. Why did we divide Fe by Fg to compare? Well, yeah, so by compare, I mean, how many times bigger is the electric force compared to the gravitational force? So if I divide Fe by Fg, that is how many times bigger the electrical force is compared to the gravitational force. And actually, Devon answered that in a much more succinctly and clear way than I did. There's another question. Sarah, to determine the scalar, how much bigger the gravity? Yeah, okay, that's also an answer. So you're answering the questions before I ever get to them. Well, that's good. Okay. So I did that experiment with the two spheres earlier on, while I was sitting here before class. And I know that the masses of those two spheres, they're 5 grams each. They're very light. The two strings that I had them hanging from, you couldn't quite see the length, but they're 40-centimeter long strings. And when I did my earlier experiment, it was about the same here. There was a couple of degrees. Each string was hanging at 2 degrees to the vertical rather than vertical once they were charged. So I took those numbers to try and calculate the forces and hence the on the spheres. I drew here a picture of the situation. So string on the left, string on the right in black. In blue, charge on the left, charge on the right. I know the masses of the two spheres. I know the lengths of the strings. They're both 40 centimeters. I know the angles between the strings and the vertical due to the repulsion between the two charges. So I know all those things. There's one thing I calculated before I went on and worried about electrical forces and electrical charges, and that's actually the separation between these two charges. So this separation, I call it R here, it's twice, see this side of this right angle triangle? That's opposite the 2 degrees. And then there's another side of a right angle triangle that's opposite the 2 degrees. So the lengths of these sides are the length of the string times sine of 2 degrees. And so if I want R, the separation of the charges, it's just twice L sine theta. And so that little bit of trigonometry tells me that the charges are separated by 2.8 centimeters, 0.028 meters. So that's going to be a number that I'm going to use as I work through the problem. Okay, so before I figure out the charge on each of the spheres, I'm going to figure out actually the force, the electrical force between the spheres. And to figure out the electrical force between the spheres, I'm going to think about the equilibrium of the forces in this situation. So let me just sketch that, and that's what I've done over here. So here's one of the charges. This guy here. Oh, didn't mean to do that. here's one of the charges. It's experiencing three forces, actually. There's gravitational force straight downwards. There's electrical force of repulsion. This is the left-hand charge, so it's a force towards the left. And then in the string, there's a tension force. And these three forces are in perfect balance with one another. They're in equilibrium, and that's why it's hanging at 2 degrees. And here, I'm describing that equilibrium. And this is something we did, you know, all the time in physics 211, and now I'm using it in physics 213. There's an equilibrium of forces on this charge that says that the gravitational force plus the electrical force plus the tension force all add up to make 0 net force. Otherwise, the charge would be moving around. Now, I can take that equilibrium and write out 2 equations that describe that equilibrium in the horizontal and vertical directions. And so that's what I did below here, these 2 equations. So in the vertical, it must be that the downwards gravitational force, Fg, is counteracted by the vertical component of the tension force, T cosine theta. Those must cancel out. And in the horizontal direction here, it must be that the left-directed electrical force is canceled by this component of the right-directed tension force. It's canceled by T sine theta. Those must cancel out too. And this is, if you think about it, this is 2 equations with 2 unknowns. So in these equations, we do not know, and we're going to figure it out, the electrical force. But we also do not know the tension force. And so we have to combine the 2 equations to solve for the electrical force. And so that's what I'm going to do on the next overhead. Okay, so here's my calculation of the electrical force. And then from this, I'm going to calculate the electrical charge. So we're starting with the electrical force. And it's basically a matter of, this 0 here should be up here. It's basically a matter of combining these 2 equations together for the equilibrium to find a formula for the electrical force. So the second of the equations, which corresponds to the horizontal direction, this one here, I can rearrange that the electrical force is equal to the tension times sine theta. And then I can use the first equation to eliminate the unknown tension. We don't know the tension. I can replace it by using the first equation, the gravitational force divided by cosine theta. So that's what I did here. And then at that point, I've got an equation for the electrical force in terms of the known gravitational force and the known angle of the string. It's just the gravitational force times the tan of the string's angle with respect to the vertical. So the gravitational force, the weight of those objects, they were 5 grams, that's 0.049 newtons. And the angle was 2 degrees, so it's tan of 2 degrees. And if we calculate the force then, it's this tiny force here. It's a 1.7 millinewtons force. That's the electrical force on the charges. So the forces are tiny. That's what makes Coulomb's experiments difficult. So what makes our experiment difficult. But now we've got that force. And then now I can calculate the charge. So to calculate the charge, I'm just going to take Coulomb's law. Okay, so that's this law here, which tells you the force in terms of the charges and the separations of the charges. I've got 2 charges Q separated by some distance r, and I'm going to rearrange it as an expression for the charge, which is the quantity I don't know, in terms of the force, which is the quantity I want to, I've already figured out. So I rearrange Coulomb's law here. The charge is equal to the force times the square of the distance between the charges divided by the Coulomb constant, and then we take the square root of that. And all these numbers I know, so I plug them in. Here's the force of 1.7 millinewtons. Here's the distance squared, 2.8 centimeters squared. Here's the Coulomb constant characterizing the strength of electric forces. And I get a charge. I get a charge that's 12 newtons, 12 nanocoulombs. It was indeed a tiny charge that I deposited onto those two spheres and made those two spheres repel. But anyway, that's an example, second example, illustration of Coulomb's law. Okay, I want to get onto superposition principle and an example illustration of superposition principle. So I'm keen to do this, and I hope I can cram this into the next half an hour. Yeah, that should be fine, I think. Okay, firstly, what is superposition principle? I see a question. Do we use 9 times 10 to the 9 or 8.99 times 10 to the 9? I would, you know, that depends on whether you wanted a very precise answer or not a very precise answer. Typically in my questions, 8.99 and 9 are the same. I think using 9 is fine. If we wanted a certain precision, if I was going to be strict about a certain precision, I better tell you I'm being strict about it. So I hope that answers that question. How would you solve it if the charges were not equal? That's a really good question, actually. And the only way we could solve it was that those were two equal spheres that accumulated two equal charges. If the charges weren't equal, then there's all sorts of possibilities that could lead to the same force. And so you wouldn't be able to solve it unless we worked with the charges being equal. So it's the only way I can solve that problem. Otherwise, there's kind of three unknowns in the problem. There's, you know, the unknown tension, the unknown electrical force, but there's the unknown ratio of the two charges. So you can only solve that problem by assuming the charges are the same. That's a really good question. That's a really good point. Principle of superposition. This simply means, simple idea really, that the total force on a charge, if it's surrounded by some neighboring charges, is equal to the vector sum of the individual forces from the individual charges. So here's an equation describing that. So supposing we've got a charge labeled 1 in the center here, another charge in the neighborhood labeled 2 upstairs here, another charge in the neighborhood labeled 3 downstairs here. The force on charge number 1 due to the neighboring charges 2 and 3 is the sum of charges 2 force on charge number 1 and charge 3's force on charge number 1. Remembering that these are vector sums. We're adding vector forces. We're adding up vectors here. I've pictured it in this case, right? I must have drawn the situation where charges 1 and 2 are unlike charges, opposite charges, because it's an attractive force between them. So in green here is the force of charge number 2 on charge number 1. In orange here is the force of charge 3 on charge number 1. They must be like charges because they're repelling one another. And then this turquoise force, I just called it F1, is the sum, the vector sum of these two individual forces. The force of 2 on 1 that I denoted F21, the force of 3 on 1 that I denoted F31 gives a total force on 1 that I denoted F1. Here I'm just showing you how that vector addition works. So, if you want to picture the vector addition, if you want to draw the vector addition, just draw the first vector, so F21. And then at the tip of the first vector, draw the second vector, F31. And then the resulting force runs from the tail of the first vector to the tip of the second vector. So the turquoise force here runs from the tail of the first vector due to charge 2 to the tip of the second vector due to the charge 3. And so that's superposition. The superposition principle applies to gravitational forces as well as electrical forces as well as magnetic forces, to all forces. Okay, so I want to look at examples of superposition. And the first example is a quiz. So we got two positive charges on the x-axis, labeled Q1 and Q2, here and here. And the question is, where we should put a third positive charge such that the net force on that charge is 0. Well, look, you can't put it over here in this region, A, because if it's a like charge, both of these charges, Q1 and Q2, will be attracting it towards will be repelling it towards the left. So the forces can't cancel out over here. If we put charge Q3 over here on the right in region C, both of the forces from Q1 and Q2, which are the like charges, will be pushing it towards the right. So those can't cancel out. But if you put it somewhere in between, and where in between depends on the sizes of the charges involved, Q1 and Q2, you can arrange that the repulsive force from Q1 on the left and the repulsive force from Q2 on the right, they can cancel out. And so the right answer is that you've got to place it in region B. I want to look at an example of superposition in a calculation. And the example I want to look at is an interesting problem. Think about, as an example, a salt crystal. So if you know a salt crystal, sodium iodide crystal, it's made of sodium ions and chlorine ions, positive sodium ions and negative chlorine ions. And they're kind of arranged in a lattice arrangement. And you can see that lattice arrangement here. Now, in a sodium chloride crystal, there are equal numbers of positive charges and negative charges. And if there's positive and negative charges, you would think, and we know, right, there's both attractions and repulsions. And you might think that, well, if I got equal numbers of positive and negative charges, why don't the attractions and repulsions just cancel out and the salt crystal fall apart? Why is it held together? Why is it bound together? And so we're going to explore a problem that kind of tells us why matter that is neutral, like the salt crystal is neutral, but containing equal numbers of positive and negative building blocks, like the salt crystal contains equal numbers of positive and negative building blocks. Why it's held together, why it's bound together, why it's stuck together. Okay, so rather than work with an entire salt crystal, I'm going to work with what we call a nano-crystal. It's about the tiniest crystal of sodium chloride you can make. And here it is. So it involves 4 ions. In purple are the positive sodium ions in the top left and bottom right corners of the nanocrystal. And in green are the negative chlorine ions in the top right and the bottom left. And they're separated by a spacing, a distance that we call a lattice spacing, but it's just the distance separating the ions. And I call that A. Here's A. Here's A. And the diagonals, because this is a square lattice, a rectangular lattice, the the diagonals by Pythagoras' theorem is just root 2a is the distance between the two sodium ions or between the two chlorine ions. And we're going to calculate the force on this top left sodium ion. So that's our plan. That's our goal. So let's see if we can do that. Okay, so the first thing I did was I wanted to make a little sketch. I want to make a little drawing of the forces, the individual forces that are acting on that top left sodium ion. So this is quite a busy drawing, but it's just to put the forces, the individual forces on that top left sodium ion. If you took 211 with me, then you know I'm really keen on making sketches, making drawings of your physics problem. And here, making a sketch, making a drawing of the forces on that chlorine ion, on that sodium ion are really important. And so let's just work our way through this sketch. There are three force vectors, three force arrows on this sketch. And they're corresponding to the three forces of the three other ions. Over here, top right, down here, bottom left, and over here in the far corner, bottom right. So I'm drawing three vectors. There's an attraction, it's this guy here, between the chlorine ion and the sodium ion at the top. There's an attraction between the chlorine ion and the sodium ion. Here's the chlorine ion at the bottom. And there's a repulsion between the two sodium ions that are at a diagonal here. And so those are the three forces. Two attractive forces between opposite charged chlorine ions and one repulsive force between the like charged sodium ion. Now, actually, I've added to the picture where I labeled the three forces as F1, F2, F3. I've added something that's kind of convenient in this problem to work with, that's useful in this problem. I've defined a force strength that is kq squared over a squared. So this is k times the charges on the ions squared divided by the separation, this short separation between the ions. So that's actually the strength of the force. This guy here is the strength of the force that's exerted between the bottom chlorine ion and the top sodium ion, and the right chlorine ion and the left top sodium ion. So that both F1 and F2 have this strength, F. I'm just going to call it F. The strength of the force between the two sodium ions, on the other hand, is weaker. Now, the charges are the same size. It's not that makes it weaker. It's the fact that the distance is greater. The distance is root 2 greater, so the force, the strength of the force, because it's an inverse square law force, is actually 2 times smaller. And so that's what I've indicated here, that force number 3 between the two sodium ions, that strength is only half of F. And so to say F is just a convenient language for setting up this problem, because all the three forces come in units of F. The two forces from the two chlorine ions are simply F in strength. The force between the pair of sodium ions, that's half F in strength. So it's a very convenient language. So I've got the drawing, I know the directions of the forces, and I actually know the relative strengths of the forces. And that's an important step in this problem, making that drawing and making that identification about the relative strengths. Okay. So all I did on this slide, first of all, is just to redraw that picture, just focusing on that sodium ion and the three forces that are acting on it. That's all that's important to me now, stripped off the other ions. So we've just got this sodium ion. Imagine I'm this sodium ion and I'm feeling these three forces. That's what's going on here. And now we just got to do the more mathematical side of this problem, which is the vector addition of the three forces. I've got this in two slides, in two parts. So this is slide number 1 on the vector addition. There's going to be a slide number 2 on the vector addition. Let's work through these. Okay, so how do we add vectors? Well, think way back to that thrilling Physics 211 lecture that was on adding together vectors. One way you can add together vectors, the general way of adding together vectors, is to break the vectors down, the individual vectors down into their XY components. And then you can add their X and Y components, and then ultimately you can find the magnitude direction of the resulting force. So that's the procedure I'm going to use here. I'm going to break these three vectors down into X and Y components. I'm going to add up their X components. I'm going to add up their Y components. Then I'm going to find the magnitude and direction of the resulting force. That's the plan. So here's where we start. We got to figure the X and Y components of F1. That's this guy up here. F2, this little guy down here, and F3, this one over here. So let's go through and do this. F1 is easy, right? Just look at the picture. I'm going to think of the direction towards the right as being, what's going on here? This is going to be the positive X direction. The direction up, I'm going to think of that as the positive Y direction. And I'm going to write down the forces in this convention for positive X and positive Y. What have I done? Have I gone on an extra slide? Yes, I did. Accidentally, I went too far. I got to go back. Here we are. Okay, so the force F1 is simply towards the right, so simply in the positive X direction. Actually, I just see a question. How did you figure F3 was 0.5 F? Was it given? No, it wasn't given. If I go back, I figured it because for F3, the separation is √2 times A. For F1 and F2, the separation is just A. So this separation for F3 is √2 times bigger than the separation for the two other forces. And since the force is an inverse square law, it means that √2 squared, that's 2 times bigger. Inverse means that the force is half as big. So it's just the inverse square law that told me this is 0.5, just to be clear on that. Okay, back to figuring out the components of the forces. So because F1 is just horizontal towards the right, F1x, the X component of F1, has a size of F and a sign that's positive because it's in the positive direction. And F1y, which is the component in the vertical direction, that's 0 because there is no component of that force in the vertical direction. So that's easy. What about the components of F2? Here's F2. Oh, I keep doing this. F2 is, if you look at F2, it's just vertically downwards. So F2 has no horizontal component, doesn't have any component towards the left or right. F2 doesn't have any horizontal component, but F2y does have a vertical component, and that's downward, so it's minus F. The entire force is vertically downwards. So that's the y component of the force F2. And then finally, F3. Now, F3 is a little more complicated. If you look at it, it's obviously got both a horizontal and a vertical component to it, because it's at 45 degrees to the horizontal or 45 degrees to the vertical. So if we want its horizontal component, I've got to take its magnitude. Its magnitude is half F. And I've got to multiply it to get the, gosh, if I could do that one more time, I'm going to jump out the window. To get the horizontal component, I've got to multiply the magnitude of that force by sine of 45 degrees to get the horizontal component of the force. The minus sign here is because I spotted it, it's in the negative x direction. So that's the reason for the minus sign. Well, sine of 45 is 1 over the square root of 2, 0.7. And then 0.7 times the 0.5 is 0.35. And so that's the component of the third force in the x direction, minus 0.35 F. And then for its y component, we'll look at its y component. It's upwards. I did it one more time. I am going to jump out the window. Its y component is going to be the cosine of 45 degrees to get the vertical times the strength of this force. It's in the upwards direction, so it's positive times the strength of the force times the cosine of 45 degrees. Cosine of 45 degrees, 0.7. I'm going to get plus 0.35 F. And so that's the components of the third force. Now, if you step back and look at this slide, I've got the x and y components of the first force, F and 0. I've got the x and y components of the second force, 0 and minus F. I've got the x and y components of the third force, minus 0.35 F and plus 0.35 F. I've got all those components now. And so that's stage one of the vector addition. There's a question, how do we know when to use sine and cosine? Well, I labeled this angle as 45 degrees. Then, but also actually the upstairs angle is 45 degrees. In this case, I wasn't very careful. You can use sine and cosine because they're the same angles. Sine always refers to the opposite and cosine the adjacent side. So if it wasn't 45 degrees, I would have had to been careful about that. Okay, so now I know the components of the vectors. I can add those components to get the resulting components of the total for the total force. And that's what I've done in these two equations here. So the resulting force, I've indicated it in black here. It's this guy here. Oh. Here's the resulting force from the vector addition. Its x component is the sum of the individual x components. And its y component is the sum of the individual y components. So I've just got to add them up. Here I am adding them all up, and I get a total x component that's 0.65 F, total y component that's minus 0.65 F. And so that's the resulting force in x and y component form. Then if I want the magnitude, all I've got to do is take the square root of the sum of the squares of the x and y components. And so I get 0.92 F, and then I filled in the expression for F. And then if I want the angle, well, I just got to take the inverse tangent of the ratio of its x and y components, y and x components. They have the same magnitudes, but they have opposite signs. And so I get the inverse tangent of -1. This 45 degrees, minus 45 degrees. This guy here is 45 degrees below the horizontal. And so I've found that force between the that sodium ion and the three other ions. And so that's the answer to this problem. We've used superposition principle. We solve for the size of the force. We know it's towards the center of the crystal. If you were to do it for all of the crystals, obviously I'm not going to do it for all of the crystals, but here it is, you'd find that all of the crystals are experiencing a force pulling them inwards towards the center of the crystal. And that would be true if you had a big crystal rather than this silly little crystal. They'd all be pulled in towards the center of the crystal. And so that's the answer to that problem. That's why crystals stick together, because although they're made of equal numbers of positive and negative charges, the net force on those ions inside the crystal is pulling them towards the center of the crystal. Anyway, that's the end of today's class.